Today we are going to see about closure properties of a context-free languages. So there are 5 properties are there. Before that we are going to see what is context-free language. In a formal language theory, context-free language is a language that is generated by a context-free grammar. There are 5 properties. Context-free language are closed under union, are closed under concatenation, are closed under clean closure, but are not closed under intersection, are not closed under complement. So first we are going to see the context-free languages are closed under union. If L1 and L2 are two context-free languages, their union or L1 union L2 will also be context-free grammar. A grammar G1 generates a set of languages L1 and a grammar G2 generates a languages L2. For example, L1 is equal to A power n, B power n, C power m, where m greater than or equal to 0 and n greater than or equal to 0. L2 generates set of languages A power n, B power m, C power m, where n greater than or equal to 0 and m greater than or equal to 0. L3 is equal to union of L1 and L2. So we are combining both the strings. The condition is same, m greater than or equal to 0 and m greater than or equal to 0 is also a context-free grammar. So from that language, the language L1 says number of A should be equal to the number of B's. And L2 says the number of B should be equal to the number of B should be equal to the number of C's. Their union says either of the two conditions to be true. So it is also a context-free language. So then we are proving that one set of productions S1 derives some set of strings and A1 derives a string A and B1 derives a string B. Then another one production S2 derives a set of strings and A2 derives a B and B2 derives a A. So we are combining with that is then the union B S1, then union with the S2. For that union we are using this OR symbol. So we are combining both the production and we are going to generate some set of languages. So that languages are closed under union. The next one, concatenation. If L1 and L2 are two context-free languages, their concatenation L1 and L2 will also be context-free. For example, L1 generates a language, that means set of A's followed by a set of B's where n greater than or equal to 0, and L2 generates a set of language, that is equal number of C's and D's where m greater than or equal to 0. L3 is equal to L1 and L2 concatenated with the L2. So L3 generates a set of language, that is A is followed by a B and C is followed by a D. That means m greater than or equal to 0 and n greater than or equal to 0 is also a context free. So here the L1 says the number of A should be equal to the number of B's and L2 says the number of C should be equal to the number of D's. But the concatenation of L3 says A should be equal to the number of B's and C should be equal to the number of D's and C should be equal to the number of D's. So we can create a push down automata which will first push for A's and then pop for all B's and push for all C's and then pop for all D's. So it can be accepted by a push down automata, hence it is a context free language. So then we will see the example, the P1 set of production P1. So the S1 derives some set of strings and A1 derives A and B1 derives a B. The same P2, S2 derives a set of strings, A2 derives a B and B2 derives a A. Then the concatenation of both the productions are, we are combining both the strings. For concatenation we are using a dot. So S1 dot S2 we are combining both the productions. So then we are defining the set of strings for S1 and set of strings for S2. From that we will generate some set of languages. That languages should satisfy a condition of context free language. Then clean closure. If L1 is a context free, its clean closure L1 closure will also be a context free. So L1 generates a an power bn. So that means number of A's followed by the number of B's. That should be equal number of A's and B's where n greater than or equal to 0. L1 closure means it generates a number of A's should be equal to the number of B's, but it includes an empty string. So then the string, it generates a empty string or it generates a number of A's followed by number of B's. Then the language is also called as a context-free languages. Here we see the production. S1 generates a A1, A generates a B. Then our production is, that is, it is a grammar is closed. We are for a clean closure, we are generating a set of productions. S derives a S1 S, and it also generates an empty string. S1 generates a set of derives a string A and A2. A derives a string B. So we are taking this production S1 tends to A2. We are going to generate a set of input strings by using these productions. So W equal to AB. So our condition is number of A's should be equal to number of B's. If the 2 A's means the string should generate 2 B's. So the same way we are taking the first production S tends to S1 S or epsilon. We are substituting the S1. Instead of S1 we are substituting AA. For S1 we are substituting A, then S. Then for A we are substituting the value B. Then we are getting the string AB S. For instead of S we are using the S1 S, S1 S. Then finally we are deriving a string A followed by a B, A followed by a B. So this is also a context-free grammar. So here we are using the derivation, that is leftmost derivations we are using here. Then intersection. If L1 and L2 are two context-free language, their intersection L1 intersection L2 need not be a context-free grammar. So for example, L1 generates a set of string, number of A's should be equal to the number of B's. Then end with a C. N greater than or equal to 0 and M greater than or equal to 0. L2 says the number of A followed by a B power n, C power n. That is, number of B's should be equal to the number of C's. The condition is greater than or equal to 0 and M greater than or equal to 0. We are generating a language L3 is equal to L1 intersection L2. We are generating a intersection. So that means the number of A's and B's and C's should be equal. All are equal. All A's should be equal to the B. B should be equal to the C. So it is not any. It need not be a context-free grammar, context-free language. Then that L1, the same thing. L1 says number of A's should be equal to the number of B's. L2 says number of B's should be equal to the number of B. Their intersection says both the conditions need to be true. But push-down automata can compare only the two. So it cannot be accepted by the push-down automata. Hence it is not a context-free grammar. Proof. We are proving that one. Grammar for L1 is we have a set of productions, and L2 we have a set of production. Then we are making an intersection. Then we get sometimes we get context-free language and sometimes non-context-free languages. Thus we can say that CFLs are not closed under intersection. CFL are not, that is context-free language, are not closed under intersection. Then the complement. For complement, we note that L1 intersection L2, that is equal to L1 union L2. So if L1 intersection L2 should be equal to the L1 union L2, where L is the complement of L. If a context-free language were closed under complement, they would also be closed under intersection. If it satisfies the intersection, then it satisfies the complement. Therefore, context-free language are not closed under complementation because they are not closed under intersection. So, CFL are not closed under intersection and complementation. Okay, thank you.